Hello, good morning, class. For today, we'll be talking about kinematics. What to expect, a little bit of definitions, what kinematics is all about, and then we'll explain what displacement, velocity, and times are, and explain the concept of motions in one dimension and two dimensions, as well as appreciating the concepts of all three by solving sample problems. The intended learning outcome is hopefully for you at the end of the session is that you will be able to analyze, explain motions of objects in one dimension and two dimensions, be able to define, calculate, and differentiate between average and instantaneous velocities and acceleration, and to solve for instantaneous velocity and acceleration via calculus, differential calculus. So, kinematics is the branch of mechanics concerned with the motion of objects without reference to the forces which cause the motion. We will be dealing with the following motions, such as objects moving along the horizontal axis, the vertical motions, and of course, projectile motions. Such motions follow a path on the respective axis and will be dealing with variables or parameters such as displacement, velocity, and time, as well as its angle. Let's define those parameters. Again, displacement, as I've mentioned before, is the change in position of an object at some elapsed time or time interval. We can solve for displacement, delta x, by subtracting its final position to initial position. Let's analyze the problem again. We are to find the displacement and the average velocity of a moving car. We can solve this by visualizing it via a graph or visually drawing it. In both figures, we have established our frame of reference at point 0, our origin. If you recall, frame of reference is just the point of view from which you are measuring things. It also determines whether our velocity or displacement is either at the negative or positive value, indicating its direction. From the figures below, you can see that the car starts at 30 meters to the right of our reference point, then moves further right to point B in the positive direction. Then from point B, it moves all the way back to the left to point F towards the negative x direction. To solve for displacement and average velocity between A and F, we make use of our following formula respectively. Substituting the values will yield you a displacement of negative 83 meters or simply 83 meters to the left of our reference point, and an average velocity of negative 1.66 meters per second or 1.66 meters per second left of our reference point. As we mentioned earlier, the average velocity is simply the ratio of displacement over time interval, or the rate of change of position per unit time interval. Instantaneous velocity, however, is different. You can think of it as speed at a particular moment in time in a given direction. It refers to the velocity at a particular moment in time. The second line represents the average velocity, while the green line represents the tangent of the line for instantaneous velocity. The instantaneous velocity can be defined as the limiting value of the ratio delta x over delta t as change in time approaches to 0, or in calculus notation, it can be represented as a derivative of position with respect to time. Graphically, you can see the average velocity does not equal to instantaneous velocity, as the velocity keeps changing per unit time. But there are instances where the average velocity may equal to the instantaneous velocity. Such condition is called constant velocity, where your instantaneous velocity at any given time is the same as the average velocity. Recall our equations, respectively, for average velocity and instantaneous velocity. Constant velocity, average velocity is now equal to instantaneous velocity and thus can be represented as such. Rearranging the equation, we can also write it such that the final position is equal to the sum of the initial position and the product of constant velocity and change in time. You would know if you have a constant velocity when your position time graph yields a slope that is the same at any point in the line. Let's try another problem. Here we have a runner running along a straight line, and his time and displacement is being recorded by his coach. The final position of 20 meters and total elapsed time of 4 seconds are given. What is the runner's velocity, and should he continue running after the 20-meter mark? What is his final position after 10 seconds have passed? The problem described the runner's velocity as having a constant rate, giving us a hint that the runner has a constant velocity or has a running speed at constant rate. We consulted by dividing the total displaced per elapsed time, and substituting the values will yield you at 5 meters per second. For the second problem, we substitute our constant velocity to our final position equation from the previous slide. The initial position is 0 and the elapsed time after the 20-meter mark is 10 seconds. Substituting the given will yield you 50 meters to the positive direction. Here's a sample problem number 3. With the knowledge gained from the previous slide and your basic calculus, you should be able to at least solve these following problems on your own. You're given an expression where x is in meters and t is in seconds. The position time graph for this motion is shown below, and you have the following displacement diagram. Next up is acceleration, which is also a vector. And acceleration is simply the change in velocity over time interval. By its definition, we can solve the acceleration by dividing the change in velocity over time interval. To appreciate the relationship between velocity and acceleration, check out this graph shown on your screen. Please note that as a vector, acceleration can be a positive or negative value. A negative acceleration does not mean an object is slowing down. It just means that it's moving in the opposite direction from your frame of reference. And just like as we did with velocity, we have also average and instantaneous acceleration. Again, average acceleration is the velocity over a time interval. Instantaneous acceleration is the acceleration of an object or a particle in a specific moment in time. The instantaneous acceleration is equal to the derivative of the velocity with respect to time, which is by definition is the slope velocity time graph. Also, it is instantaneous acceleration can also be obtained by getting the second derivative of a particle's or object's position with respect to time. Let's try solving this problem. We are being asked what the average and instantaneous acceleration given the expression below. For A, we simply substitute the given time interval 0 and 2 seconds to the given expression, and substituting them will yield us at negative 10 meters per second squared. To find the instantaneous velocity in B, we simply get the derivative of the expression just like so, then substitute the specific point in time t at t seconds, which will yield you at negative 20 meters per second squared. Just like velocity, there are instances where we have a constant acceleration, where average and instantaneous acceleration are equal. Recall our equations below. At constant acceleration, now average acceleration is equal to instantaneous acceleration, and thus the instantaneous acceleration equation can be represented as such. Rearranging the equation, we can also write it such that the final velocity is equal to the sum of initial velocity and the product of constant acceleration and change in time. You would know if you have a constant acceleration when your velocity time graph yields a slope that is the same at any point of the line, and when velocity varies linearly. Where you can solve for V average at the sum of the final and initial velocity over 2. Substituting the equation from our previous slides, we can rearrange the equation to find another way to solve the final position at constant acceleration condition. With the equations and concepts you've learned, you should be able to solve the sample problems provided. Give it a try before you review your solutions with mine. By now, we've dealt with problems moving along the x-axis. The next lesson is called free-falling objects, where we're dealing with objects with motions moving along the vertical or y-axis. We call it free-falling object, in which the object is subjected solely to the influence of gravity. When working such problems, we assume the following. Air resistance is neglected because the object is often thrown or launched relatively close to the Earth's surface, where air resistance won't even take effect no matter. And number two, variations with gravity g with respect to the changes in latitude is neglected for the same reason with number one. The working equations we have on objects moving along the x-axis will work too in y-axis since they're moving in one dimension only. And just note, instead of the x-axis, we use of the y-axis station, and your acceleration is equal to the acceleration due to gravity with a negative sign denoting the downward direction. Here are a summary of the equations we've discussed, and may they serve as your guide in solving kinematic problems in one dimension. Using our known kinematic equations, we can now solve the problems A and B easily. Okay. Let's try sample problem number 6. We have a problem stating that a stone is thrown from the top of a building given an initial velocity of 20 meters per second, straight upward. And the stone is launched 50 meters above the ground, and the stone just misses the edge of the roof on its way down. Find the following. We can easily solve problems A and B easily by substituting the given and using the following equations, and you should yield with 2.04 seconds for the time required to reach the maximum height, and the maximum height at 70.4 meters. Try solving for C and D on your own before comparing each other's solutions. Moving on now to the last part of the lecture, which is motions in 2 dimensions. These are motions that where changes are occurring when a particle accelerates in 2 dimensions. Changes may involve changes in magnitude and velocity with time, the direction of velocity vector with respect to time, even if its magnitude remains constant, with both magnitude and direction, the velocity vector with changes over time. A lesson back on vector quantities will be essential in dealing with the motion problems in 2 dimensions. Here is a familiar vector components and its resultant represented by such equation, where x, y, and r change with time as the particle moves, while the unit vectors I and j are unitless and remain constant. I and j represents the x and y axis. So the motions in 2 dimensions can be modeled as 2 independent motions in each of the 2 perpendicular that are associated with the x-axis, such that any influence in the y direction does not affect the motion in the x direction and vice versa. If you recall, you would know that vector quantities has rectangular components or several components. A velocity vector in 2 dimensions can be expressed in such a way where velocity vector is equal to the sums of the products of x, y velocities and I, j unit vectors, respectively, represented as such. The unit vectors represent the x and y axis. We can expand it further by substituting the velocity equation, which would yield an expression like so, and the final velocity vector at constant acceleration. A common example of a 2-dimensional application is a projectile motion. To define it, say you have a cannonball to be launched in a cannon at an angle. The cannonball here is the projectile. It is the object with which it will travel a curved path. And the cannonball will take a path called a trajectory. It is the path at which the projectile travels. It will travel on a curved path before hitting the ground. As we described it before, two-dimensional notation can be modeled independently. Hence, we can solve projectile motion problems using previously derived equations for motions moving along the x and y axis respectively. Moreover, you can solve the maximum height and the horizontal range of a projectile by using the following equations. You can also take note of the following equation shown on your screen to solve for the maximum range of the trajectory. Again, please note that the direction and frame of reference matter as this affects the signs of our vectors. Let's try solving for problem number 7. Here, we are given the initial velocity for the x and y, time, and acceleration for the x component. To determine the total velocity vector at any later time, simply use the expression shown, then simplify. You should be able to acquire this expression. Now, to calculate the velocity at the particle t 5 seconds and its angle it makes on the x-axis, we use the acquired expression from A, substitute 5 seconds to t, and you should be able to get the velocity components 40 meters per second and negative 15 meters per second, like so. Knowing this, you may now solve the final velocity and angle using previously known equations during our vector lecture. You should be able to get 42.72 meter per second and 20.56 degree in the x-axis as your answer. Now try solving C on your own. With your new understanding of equations for motions in 2 dimensions, you should be able to solve the following problem. Try it on your own and compare your answer with your instructor. Final reminders. You may begin solving PPE number 2 in your lecture 2, Kinematics found in your G-Drive folder. Deadline will be on Tuesday, March 8, 2022, 11:59 p.m. PPE number 2 will be a group effort as well. PPE number 0 solution will be provided once the mission is complete. Again, to submit your PPEs, kindly forward as image file to your class rep or class secretary. Class rep or class secretary will compile and save them on their G-Drive folder. Finally, the G-Drive folder will be shared to me. All future submission will be done the same in the absence of my USD email address and Blackboard account. Thank you so much.